facilities, and I'm based here in Oak Ridge, Tennessee. The height of summer feels very similar to here, hot and humid, but we get some relief later in the year. So our mission is basically to enable computational sciences that would not be available to do if you didn't have these leadership class computing facilities. And just as also a bit of an advertisement, access to OLCF, that is us, and the Argonne facilities are actually open to researchers from all over the world. There are applications that can be submitted. The deadline for this year has passed, but there are annual times. If you have interest in this, certainly come and talk to me or contact our center. This is where we are, in the middle of the mountains in Tennessee, and we also have a very nice experimental neutron facility. But I'm going to talk about, start out with giving you an overview of statistical mechanics, to see what is the problem, what are we trying to solve, why it's important, and then what are the particular challenges that we are facing, why we are interested in efficient sampling techniques, and then I'll describe some of the sort of crude methods we've come up with to improve the sampling. And I'm certainly will encourage you to suggest better ideas, improvements, or suggestions on how to actually make what we're doing more robust, or have a better understanding. So statistical mechanics really got its start with Ludwig Boltzmann and his very famous equation that actually will feature throughout the talk, and that is engraved on his gravestone in Vienna. So what are we doing in statistical mechanics? We describe the behavior of a system that is a large ensemble of particles that give rise to something that is macroscopically observable. So a piece of material contains 10 to the 23 or so atoms, but they all behave together collectively. There's no way you could describe all the trajectories using the laws of physics, Newton's equations, Schrödinger equation also directly. So we want to have a statistical description of how this system behaves, and basically all the coordinates of the physical system are described with these phase-space coordinates, and they might be for a particle the position they have, the momentum they have. Atomic species, what is it? If you have an alloy, it orders different atom types exchange positions. The magnetic moment, if you want to describe a magnet, and many more. But the dimension of this phase space is really large. As I said, there are 10 to the 23 or so atoms just in a small piece of material, and position and velocity, for example, are 6 coordinates, you have a phase space that is 6 n-dimensional. So how do we extract information from it? And the really fundamental function in all of physics is the Hamiltonian, and that is the energy of the system that maps this phase space to a real number, which is the energy. This function has a lower bound, so we know it's always there's a finite minimum, and we'll start from there. So and this lowest energy state is what the system will be in at, by definition, absolute zero temperature. Now, this is something that is not really very useful for this understanding what a system really does at finite temperatures, 300 Kelvin, 270 Kelvin or so. So at a finite non-zero temperature, a system is in some state out of this phase space, and the probability to be in a given state is given by this Boltzmann distribution, which depends on the energy, and beta is the inverse temperature. And then if you want to measure anything, any observable magnetic moment, specific heat, polarization, internal energy, these are all averages of this instantaneous value over the phase space with the probability density that is given by this Boltzmann distribution. So this is a very highly dimensional integral that you really can't evaluate for anything but the smallest model system of perhaps a handful of atoms. And this is actually also the very original application of Monte Carlo sampling of the Metropolis algorithm. Metropolis Rosenbluth-Teller's paper was basically sampling physical distributions. So there are basically in statistical mechanics different approaches to describe this. So one is what's called the microcanonical ensemble. You consider a closed, isolated system at a constant energy, then the entropy of the system is exactly this formula that you've seen on Boltzmann's gravestone. In this description, actually, temperature is a derived variable, and it's basically related to the slope of the microcanonical entropy. More commonly, physicists think in terms of the canonical ensemble, or if the particle number is not conserved, which we're not going to talk about here, grand canonical ensemble. There we have a system that is not totally insulated from the environment, but is in has some energy exchange by being connected to a heat bath. And there, the states, the energies in the system are distributed again according to this Boltzmann distribution, and ultimately you can find most of the things you're interested in once you know this partition function, which, as you saw, was actually the normalization of the probability density. So this is just again repeating. Once we have the partition function, we get the free energy of the system, which is basically the log of the partition function. And basically all observables are derivatives of this free energy with respect to the associated field. So if you're interested in expectation values of the magnetism of the system, instead of doing the sampling over the instantaneous magnetization of the system with this probability density that I showed 2 slides before, you can also take the derivative of the free energy with respect to the magnetic field, and the value at zero field is the expectation value of the magnetization. Not going to talk about how to use Metropolis to sample from this distribution. I mean, that's a very standard approach, but a method that has become fairly popular in statistical mechanics, and that is the Wang-Landau method that was introduced by Ferdinand Wang and David Landau about 17 years ago. What we do here is, instead of, since we're interested in actually the behavior of the system at many different temperatures, so if we want to know, at what temperature does magnetization vanish, at what temperature does a material order melt, or whatever, we need to run these simulations at many temperatures, so that becomes very expensive, especially if you don't really know what is the temperature range we should be looking at. Instead, we want to calculate the density of states of the system, this G of E, which is basically how many, the number of states at a given energy. And if we know this, then we have this equality, so the sum over all the states with this weight is just the integral over the number of states at a given energy with this energy factor, so it becomes a one-dimensional integral, and there is some normalization factors, as we'll see, that is actually not very important for most physical observables. So now we need to, if we knew this G of E, this density of states, we could calculate the behavior at all temperatures of a system very cheaply. So how do we find this G of E? And one approach is this Wang-Landau method, where you realize where the starting point is that if you sample from phase space with states with a probability that's now proportional to the inverse of the density of states, you will basically find all energies with the same probability. So you get a flat energy histogram. So to do this, we start out by an initial guess for the density of states. For lack of better knowledge, we assume it's constant, and some update factor. We propose a move, and we accept or reject the move based on the ratio of this G of E at the start at the energies of these 2 points, and then we update the density of states by multiplying it by this update factor and record which energy we've visited. And we repeat this until we get a sufficiently flat histogram, and then we reduce the update factor f and repeat. It's until we basically have a converged density of states. It's easy to see that the correct G of E is a fixed point of this method. It's not quite clear to see that it always will converge there, though. But in practice, it works, and that's what for us physicists usually matters. So if we now know this G of E, we can calculate, as I said, the partition function, the free energy. One thing, though, is, as I pointed out, there's this normalization G naught, which we don't get out of this algorithm. So we get the density of states up to a multiplicative factor. And it turns out that it's a constant shift in the entropy or a linear term in the free energy, but these are quantities that are not really directly measurable. What is actually directly measurable are things like internal energy, specific heat, and so for those, fortunately, this normalization factor G naught drops out. So basically everything that is really physically, experimentally observable does not depend on the normalization. So all this works very well if you have a very cheap and easily to evaluate Hamiltonian, if it can be done fast. So standard models that usually looked at are Ising model or simple Leonard-Jones model or so, where it takes milliseconds to evaluate the energy even for large system. But we really want to combine this with not a simplified model of physics, but with something that actually allows us to predict the behavior of a real material. What we are using often is density functional theory calculation to find the energy of the system, and that is basically a way of solving the Schrödinger equation of the system. So getting the energy now is the smallest eigenvalue of a partial differential equation, and the x's, the state vectors, are actually constraints that enter this the solution of this partial differential equation. I'll have an example later on from magnetic system that illustrates this a bit better, but this means is very expensive. So instead of milliseconds, it now takes hours of CPU time to evaluate just one probability, just one evaluation of the energy. So anything we can do to reduce the numbers we need to evaluate the Hamiltonian, we need to evaluate the energy of the system, and hence the probability of a state really will significantly save computational resources. Even in Oak Ridge, where we are blessed with currently the fastest computer in the world, at least that's publicly known, this is still a huge challenge. And to illustrate how actually Wang Landau is already an improvement in that regard over the standard metropolis sampling, I'll show you here some old work from my collaborator Ying Wei, where she looked at a very simple lattice protein model and performed the simulation both with Metropolis and Wang Landau, and ran the simulation for the same amount of CPU time. Ultimately, the Metropolis method will also find the low temperature structure, but because of the difficulty in sampling the energy landscape at low temperatures, it will require significantly more computational resources to get there. So that's already a good step. So that encouraged us, and we went, can we find the Curie temperature, the temperature at which a magnet becomes non-magnetic, completely from first principles, without mapping to a model. So here we basically introduce our phase space R, the direction at which the magnetic moments on each atomic side point, and then we solve basically the density functional theory with these approximations to the density of states, and find to the, oh, sorry. This can be confusing, that two densities of states. When physicists talk about this, there's the electronic one, which we don't really care about, except that it's required in solving the Schrödinger equation, with a constraint that ensures that the moments point in this randomly chosen direction. If you just solve DFT without this constraint, you always will find the zero temperature ground state. So running this, and that was a few years ago on the predecessor of the Titan system for 250 atom simulation cell. We ran for about 5 million CPU hours, and we find actually a very good agreement as far as the physics is concerned, without any assumptions about the system, just saying, oh, it's Ein, it sits on a BCC lattice, and out comes the Curie temperature of the system is 980 Kelvin. Experimentally, it's 1050. Similar for cementite, iron 3 carbon, we have similarly good agreement. So everything is fine, isn't it? But this was still a fairly small system, and fairly simple. And for the Wang Landau algorithm, we had to introduce some sort of energy bins. What is the size of the bins to choose to begin with? So we asked ourselves, can we avoid binning? Can we sort of construct the density of states as an expansion in terms of some basis functions that will actually make it much easier for us to manipulate it also in terms of doing this microcanonical analysis, finding the derivatives of the DOS to get the temperature and specific heat and things like this. So the ansatz we've chosen there is we expand log of G. And, okay, I didn't really point this out, I think. What Boltzmann called W is our G. So log of G is the microcanonical entropy. And we expand this in terms of some orthonormal basis. And now we sample, generate energy samples by drawing from the phase space and accepting and rejecting them based on the same acceptance probability that we used for the Wang-Landau algorithm. But we're not going to directly update the G right now. We just collect them and see if we can use this knowledge to find a correction to our initial guess of the DOS to get an improved version. So that's what we're doing. Expand our guess for the density of log of the density of states, and we also have some correction factor that we assume that we can expand the same way. Again, for lack of better knowledge, and we might have better knowledge, we start out with some guess. We generate a set of energies, assume them to be sorted, and then sort of the magic happens in step 4, which will come on the next, I mean, not really magic, but most of the work is done in step 4, where we find the expansion of log of C to update the G. And we repeat this until C is basically indistinguishable from random noise around 0. So instead of having the histogram, we now think in terms of the distribution function here, which is essentially just the integral of the histogram. If we knew that our guess for the DOS was right, we basically would get something that's consistent with a straight line. In practice, since we have a guess that's off, we'll get something that looks something like this. So we subtract the straight line and we get some remainder, which is either just noise around 0, then we are done, or looks something like this. Sort of thinking backwards, so if we the histogram would be the derivative of this distribution function. So the correction that we need to apply, and that comes from another sampling method that I haven't mentioned called multicanonical sampling, where you basically update the DOS with the histogram that you've accumulated we find that the update we should use is the derivative of this C of E. So we try to find an expansion of the remainder in terms of some additional some additional basis set that is related by being the derivative that we can expand its derivative in terms of easily in terms of the original basis set phi, and thus find an expansion of the derivative, and this gives us then the correction factor. Now, some examples of what we got out of this. First test case is actually not high dimensional but one dimensional. Use this to do just a Monte Carlo numerical integration of a 1D function, and comparing this with, actually there's also a Wang-Lambda way of doing this integration, and the very simple function we've chosen is just x squared between -2 and 2, and in this case we actually can find a closed form expression for the DOS given up here. So if we now expand both C and G in terms of sine and cosine functions, we basically get the same result as Wang-Lambda in order of magnitude fewer steps. Going into a bit more detail, we looked over how does it depend on the number of samples we chose at each update step. So here's 500, and there seems to be some, and as you'd expect, as you increase the number of samples you draw at for each iteration, you significantly improve the results. So this is 1000, which was what we had shown before for the DOS. And it turns out that sines and cosines are not really good basis for doing this, and it will become even more obvious for the physical example. We find that basically very early on the low frequency parts get locked in and basically not being updated well in this scheme. So to avoid this, we basically update them at each iteration step by doing a random permutation and updating only a subset of them, and also doing much more incremental updates. So we basically introduce some sort of mixing parameter S to don't go the whole step, but only sort of nudge us towards the correct answer. And that actually improves the convergence properties that we've observed here. So now to the Heisenberg model, which is basically a simple model that is very similar to the real physical system of the iron calculation that I showed you earlier. Is we have basically a system where the phase space is just a set of points on the sphere, and we have n of those. And the energy in the Heisenberg model is just the dot products of those with certain links between some of them that defines the geometry. So here for this we've looked at just a simple 2D square lattice and with periodic boundary conditions, and again for this test it's just a very small 4x4 system, and again using the sine cosine basis set we see it starts out very bad because it is a sort of a global basis set, so any change you do here trying to correct what the dust looks like affects everything, even the things that already are good, or where you don't have enough samples to make a good choice where to go. But ultimately we after many iterations we arrive at something that looks actually quite reasonable. So trying to see just testing is it really sort of a basis set problem, or or is there something else going on? Instead of using sine cosines, we basically represent them as piecewise constant functions between fixed energy points. Pins. I mean, we're back to where we started out essentially in terms of how we represent the functions. So even though our original motivation was get rid of the bins, we're back there, and you can't really tell very well, I think, from back there that there are actually two curves. One is the Wang-Landau results, one is the binless, what we call binless. I mean, it's no longer binless Mooke, but basically our new scheme has an improvement again of about a factor of 10 or 15 number of total iterations that we energy evaluations that we needed to get the results. So we think it might be some type of useful approach again for us to reduce the number of energy evaluations, but there are still quite a lot of things for us that we need to understand better to make this whole approach more robust. And with this, I think I want to thank you for your attention, acknowledge the funding we've had both from the LDRD program at Oak Ridge and from the Oak Ridge Leadership Computing Facility. And this work has been, original ideas have been published here, and some more detailed description of what I've showed you is currently in press and should be published soon. Thank you. Yes, but again, that's these were the two easiest for us to implement. So, as I said, that exploring what are better bases is sort of an ongoing thing, and you really want to have something that is not really globally, you want to have a much more localized basis. So something, if you have a large change here, shouldn't affect what's happened at the other end. That actually something that we've also thought about, yeah.
Markus, at the risk of saying something wrong, could I ask, do you know the technique in statistical delayed acceptance, where they use a cheap function to decide whether they want to accept the sample or not?
Oh, yes, and actually that's also some of the things we're exploring in a separate project to see, can we build some surrogate cheap surrogate models that will allow us to march ahead in generating samples and then correct with based on the full Hamiltonian evaluation. Yeah, and that's something where we're actually working with Cody and.
Oh. If that's it, then we thank Markus again.